Hi everyone, in this video we'll be looking at examples of laws of indices, and as always the examples that I'll be using are available in the link in the description in case you want to give them a go yourself, and there's also some timings for different parts of the videos there so you'll be able to stick to a certain question. So we'll jump straight in and start the examples. Now the first question asks us to calculate the following expressions, and the first expression we have is 2 to the power of 5. So we have 2 to the power of 5 is equal to, and another way of writing this is to say we have 2 times 2 times 2 times 2 times 2. So we have 2 times 2 when we have 5 lots of 2's. So this means that we're able to simplify 2 times 2 to get 4. And then we can simplify this 2 times 2 to get 4 as well. And then we're left with 1, 2. So we have 4 times 4 times 2. And then 4 times 4 is 16. And then we're still timesing by 2. And 16 times by 2 is equal to 32. So this means we have 2 to the power of 5 is equal to 32. So on our answer line we'll write 2 to the power of 5 is equal to 32. Now the next question is asking us to calculate 2 to the power of 2 plus 4 to the power of 3. So let's write this underneath again. So we have 2 to the power of 2 plus 4 to the power of 3 is equal to, and if we just separate these two terms for a second, we have 2 to the power of 2, which is equal to 2 times 2, and 2 times 2 is 4, so this is equal to 4, and we have 4 to the power of 3, which is equal to 4 times 4 times 4, and 4 times 4 is 16, so we have 16 times 4, which is 64. So 4 to the power of 3, or 4 cubed, is 64. So that means up here we have 2 to the power of 2 plus 4 to the power of 3 is equal to 4 plus 64, which is equal to 68. So that means 2 squared plus 4 cubed is equal to 68 as our final answer. So we'll do one more example. So we've got 3 squared minus 4 squared. So I'll just write that underneath. So we have 3 squared minus 4 squared is equal to, and we'll split this up again as two different terms. So we have 3 squared, which is 3 times 3, which is 9. And then we have 4 squared, which is 4 times 4, which is equal to 16. So that means we have 9 minus 16, which is equal to minus 7. So that means we have a final answer of 3 squared minus 4 squared is equal to minus 7. So hopefully you managed to follow those 3 examples through. There's just a few questions here just to do yourself. They're just quite similar to the ones we've just done. So just give them a go and then check your answers against the solutions in the description. So next we'll move on to examples where we might not have a numerical number, it could just be a variable, so where a letter is representing a number. And the first example we have is n to the power of 3 multiplied by n to the power of 5. So if we just use the same method as what we did before, and we'll just write everything out, so we have n cubed times n to the power of 5 is equal to, well we have n times n, which is the n to the power of 3, and then this is timesed by n times n times n times n times n. So we have 5 n's there. So that means we have 8 n's all times together, so I'll just put 8 n's. And this obviously means we have n to the power of 8, as we have n times by itself 8 times. So we'll just write n to the power of 8 there, which is the answer. But when we move on to more complicated questions, we don't want to be writing out how many n's we have. So what we can say is that n to the power of 3 times n to the power of 5 is equal to n to the power of 3 plus 5. And obviously 3 plus 5 is equal to 8, so we have n to the power of 8. So then this method is obviously a lot quicker because we're not writing all the n's we have. Now this is one of the index laws where we have a to the power of x times by a to the power of y. That would equal a to the power of x plus y. So we can use this rule whenever we have the two variables representing the same number. So for this example, we have n for both numbers, so that's why we're able to use this rule. But obviously if we had a different letter, we wouldn't be able to use this rule, as the stuff here wouldn't apply. As in that case, we wouldn't have 8 lots of n. It would be so much of n, and then the other would be so much of the other variable. So we can only use this rule if we have this number and this number, or this variable and this variable, which are just representing numbers, are the same. So let's move on to another example now. So in this case we have x to the power of 4 divided by x to the power of 2. So we're doing the opposite operation than we did before. So we did multiplication before, now we're doing division. So if we write x to the power of 4 divided by x to the power of 2, this is the same as saying x to the power of 4 over x to the power of 2. It's just a different way of writing it. But when you write it like this, it's a bit easier to see what we could do. So if we write out the full thing as we did before, so we have x times x times x times x over x times x, we can see that since everything on the numerator is multiplied together and everything on the denominator is multiplied together, we can actually cancel these two x's here with two x's on the top. And then that would leave us with x times x, which is equal to x squared. But same again, there is a rule that we can use to do this a lot quicker, because if we have more complicated examples, that would take a long time. So if we have x to the power of 4 over x to the power of 2, this is equal to x to the power of 4 minus 2. And 4 minus 2 is equal to 2, so we have x to the power of 2. And if we think about this for a second, if we already know that when we multiply two variables together, and those two variables are both represented by the same letter, then we're able to just simply add the powers together. So we added the 3 and the 5 together to make 8. And then since the opposite of multiplication is division, and when we did multiply we used addition, then when we divide we also use the opposite operator, which would be subtraction. So we can sort of say to ourselves, well, when we times in together, we're going to use addition and we add the powers together. But if we're dividing, then we need to use subtraction and we need to subtract the powers. So that's why we have x to the power of 4 over x to the power of 2 is equal to x to the power of 4 minus 2, as we have this 4 minus this 2, and then that obviously gives us x squared. So we have our answer that x to the power of 4 over x to the power of 2 is equal to x squared. And then if we were to write some notation for this, we can say that a to the power of x divided by a to the power of y is equal to a to the power of x minus y. And then that's the rule that we're actually using here. Now let's move on to another example. So again, this one is also different. So we have n to the power of 3, and that whole thing is then squared. So we have n to the power of 3 times by n to the power of 3. So if we write n to the power of 3 all squared is equal to, well, n to the power of 3 is n, and then that's squared. And then again, if we simplify that, we're going to have one lot of n times n times by a second lot of n times n times n. So in total here we have 6 lots of n's, which means we have n to the power of 6, as we're times in n by another n 6 times. And then I'm sure it's no surprise that there is a quicker way of doing this, and there's another indices law we can use. So it turns out that if we have n to the power of 3, and then that's all squared, this is the same as saying n to the power of 3 times 2. And then obviously 3 times 2 is 6, so we get n to the power of 6. And this is because we have the rule that if we have a to the power of x all to the power of y, then that's equal a to the power of xy. So that's the rule that we just used here. And the way I always like to remember this one is that if we times 3 and 2 together, then the bracket sort of makes the left-hand side of the times symbol. So I just have to imagine the right-hand side, so then I know that I need to times them two together. So there's 3 examples here just for you to have a go yourself, just to make sure you understand those 3. And then we're going to move on to some exam style questions. And you can see that what we've just done is very similar to what you might be asked in an exam.